Bismillahirrahmanirrahim. Today I'd like to elaborate a little bit more on polygons. We talked about polygons last time, and I had suggested you some key features of polygons. Here I have drawn for you the ultimate non-polygons, the ultimate a figure that kind of violates every single rule established for polygons. So let's compare the definition that we established last time with this particular figure, which violates all of those features. So first we said polygons are two-dimensional plane geometric figures. What does this mean? Two-dimensional, or as opposed to three-dimensional. Polygons are not three-dimensional, they're two-dimensional. Another way of saying the same thing, that something is two-dimensional, is that there are plane figures. In other words, they're flat, they can fit in it like a plane. So you can draw them in a piece of paper, like a piece of paper being a representation of a plane. So there are two-dimensional or plane geometric figures. Now, I didn't draw this one as a three-dimensional figure, so, but that won't be that too difficult. But this particular figure doesn't violate that. Okay, that's fine. Okay, good. So there are two-dimensional plane geometric figures, all right? And then they are closed. In other words, they are not like this. There's a side missing, almost like there's what's going on over here. They're not. They are not open there. So all polygons by definition must be closed figures. Okay, so, and secondly, their sides are segments. So here's a segment side, that's fine, but this particular side is a little curvy side. It's not a segment, it's kind of like a curvy thing. So this would disqualify this particular figure as being a polygon. And thirdly, there are two special additional criteria for the sides. These segments, first, they must be non-intersecting. Okay, now this one is intersecting, so the sides here are intersecting. So this is another violation here. And they are non-collinear. So the sides can't be like, you know, like straight this way and straight right next to each other in a straight line like that. So in this particular figure, this dot here, blue dot, is meant to represent the vertex, and then this would be a disqualifying feature if that is a vertex. So because these two sides, whoever do this, that would be me, if they claim that this is a vertex, then this would be a disqualifying feature also. Now, as I suggested last time, of course, these segments are composed of an infinite number of points. As long as you claim that they're just points, that they're not vertices, that's okay. But as soon as you claim that any of these points that are on the segment are of a vertex, then that would be a disqualifying feature for a polygon, because polygon sides must be non-intersecting and they cannot be collinear. Okay, that's that. And finally, each vertex is common only to two sides. In other words, you can't have multiple sides, more than two sides coming from each vertex. For example, here you have this side and this side and this side. They all meet at that particular vertex, right? So that's another disqualifying feature. So this is a ultimate figure that is not a polygon. Okay, now this is the basic definition features of polygon that we established last time. Today, inshallah, I like to elaborate on this and speak about different types of polygons, inshallah. Okay, the first thing I like to talk about is some basic terms that are related to the polygon. Of course, we said polygon has these corners. These are the vertices. We can label them A, B, C, D, E, and as you can see, this is a five-sided polygon. I have labeled all the vertices. And naming polygon is pretty easy. You just call them P-O-L, polygon, and then just trace out the vertices, A, B, C, D, E. You could also say polygon C, D, E, A, B, or D, C, B, A, E, whichever way you trace out, but you have to go in a consistent way. You can't, you have to go either clockwise or counterclockwise starting at any of the vertex. So naming polygons is just easy. You just pick a vertex and just trace out the polygon in either clockwise or counterclockwise and using any of the vertices, and that there will all be correct names. A polygon has an interior. Everything that's on the inside is called the interior, and everything that's on the outside of the polygon is called the exterior. And in the same way, a polygon has interior angles. This is called an interior angle. A-N-G-L-E. So it has interior angles. Here's one interior angle, here's another interior angle, here's a third interior angle, and here's a fourth interior angle. Of course, this is going to be a fifth interior angle like this. So these are all interior angles of a polygon. So a polygon has interior angles that I've just labeled here, and it also has exterior angles. The ones on the outside, these are called exterior angles. Okay. And so interior angles, and then they have exterior angles. This is the interior angle, and this is the exterior angle that corresponds to this interior angle. So it has interior angles and exterior angles. And if you wanted to, not that I'm saying you should, if somebody were to draw a segment to connect any of these two, connect these two vertices like this. Not saying that this is part of the polygon, because it won't be a polygon anymore, right? Because it will violate this particular rule. But if you were to connect this just for thought processes, if you were doing some kind of problem, if you would connect these, and this would be called a diagonal. So if you connect any of the sides, that segment would be called a diagonal. So these are some basic terms: the vertices, the sides, interior and exterior angles, and a diagonal of it that goes to connect two vertices of a polygon. Some basic terms regards to polygon. Okay, so the first distinction, or the first category of polygons that we should recognize, is that there are two types of polygons. There are convex polygons and there are concave polygons. Okay, so these are different types of polygons. So I've drawn a representative picture of each type. So this is a convex polygon and this is a concave polygon. The way I remember this is that the concave polygons, they have a little cave in there. So like this, they kind of have a mouth, like a Pac-Man type mouth, or they have like a dent like this. So you can call it which way you like to call it. The concave polygon, like something dug up, like a cave, or like a dent, or like a mouth, like that they have. So any polygon that has like a dent or like a cave like this is called a concave polygon. So then now there's a more formal definition. Of course, you don't say in geometry a concave polygon is the one that has a dent in it. You know, that's not very professional sounding to begin with, right? But we should determine its more formal definition in just a second. But in more simplistically speaking, a concave polygon is the one that has, like, a mouth or dent in it, if you like to say, or like a cave in it, caves in, so to speak. And convex is the one that does not have this. More formally, you could do what's called a line test. Okay, so you could do what's called a line test. All right, that is, if you extend the lines, from any particular side, if in a concave polygon, the side would go through from the inside of the polygons. If I were to draw a line like this on top of this side, or if I were to extend this line on the other side, so if I were to extend this like this, the line that contains the side goes through inside of the polygon. A concave polygon, if you extend any of the sides, one of them at least would go through the interior of the polygon. Now, another distinction that you can make between a convex and a concave polygon is that in a concave polygon, the one with a dent over here, one of the interior angles is greater than 180 degrees. Okay. Now, if you remember, I'm going to try to draw an acute angle that's less than 90 degrees, and here's a right angle that's 90 degrees, and here's an obtuse angle greater than 90 degrees, and here's a straight angle that is 180 degrees. You can have angles that are bigger than 180 degrees, right? Like this, right? So from here to here, that's bigger than 180 degrees. It just keep moving like arms of a clock, right? So it's like go this way and 90 degrees, more than 90 degrees, 180 degrees, keep moving. This angle is greater than 180 degrees. Maybe it's, 240 or something like that, or 210 or something like that. You follow? So another distinction between a convex and a concave polygon is that at least one of the interior angles of a concave polygon, the one that's caves in, is that it's greater than 180 degrees. This angle, particularly over here, is bigger than 180 degrees, right? And that kind of makes sense. So there are two ways of determining whether a polygon is convex or concave. And to me, the easier one is that this line test. If you extend any of the sides, those lines would pass through or go through the interior of the polygon. Another way of saying the same thing would be that one of the interior angles has to be greater than 180 degrees. So that's the distinction between a convex and a concave polygon. Okay, so we suggested again there are two types of polygons: the convex polygon and concave polygons. These are both different types of polygon. It's not that one is better than the other. I'm better than you because I'm convex. It's not like that. It's just there are two different types of polygon. So convex polygon are like this, and concave polygons have, if you extend any of the sides, the lines that contain those sides would go through the interior. Maybe at least one of them would have to, go through the interior. Two actually would have to go through the interior. So that's how you determine whether a polygon is convex or concave. Okay, now naming of polygons. Now, polygons are named based on the number of sides that they have. So if you have a three-sided polygon, that's, as you're very familiar to, that's called a triangle. So here's a three-sided polygon. So a triangle is basically a three-sided polygon, correct? And that you're familiar with already. So a three-sided polygon is a triangle. A four-sided polygon, it's called a quadrilateral. Now, there are a whole bunch of different types of quadrilaterals. Square is a quadrilateral. A parallelogram is a quadrilateral. A rectangle is a quadrilateral. So all of these are examples of quadrilaterals, okay? So a triangle, three-sided polygon. Four-sided polygon is called a quadrilateral. A five-sided polygon is called a pentagon, penta meaning five. Six-sided polygon is called a hexagon, right? So triangle, quadrilateral, pentagon, hexagon. Seven-sided polygon is called a heptagon. Eight-sided polygon is called an octagon, is an octopus having 8 legs. Nine-sided polygon is called a nonagon. And 10-sided polygon is called a decagon. 11-sided polygon is called a hendecagon, or sometimes it's just called undecagon. Undecagon, like that. So 11-sided is called a hendecagon, and 12-sided is called a dodecagon. And then if you have any other bigger numbers, you can actually names for them, but like for example 17-sided, you just call it a 17-sided polygon. That's it. 17 gon, that's what it's called, 17 gon. So, or 32 gon, 64 gon, or 64-sided polygon. So any longer than that, and if you don't remember this, you just say, okay, it's a 9-sided polygon, 11-sided polygon. So do you have to memorize these? No, but if you memorize, it's kind of cool, but you don't have to. But some of these are obviously simple, and you're expected to know them. A triangle, 3-sided polygon. Quadrilateral, 4-sided polygon. Pentagon, 5-sided. 6-sided is called hexagon. 7-sided heptagon. 8-sided octagon. 9-sided nonagon. 10-sided decagon, 10-sided decagon. 11-sided hendecagon or undecagon. 12-sided is dodecagon, and then beyond that, just call it n-gon, 17-gon, 18-gon, 21-gon, etc. So these are some of the common polygons that we see, and you can remember them. I probably should know some of these, at least the basic ones. You should know, so that would be helpful. Okay, so the next thing I want to talk about are 3 particular terms: equilateral, equiangular, and regular polygon. These are 3 terms that are used to describe polygons. So there are polygons that are equilateral, there are polygons that are equiangular, and there are polygons that are regular. These terms might be a little bit tongue twisters, at least they are for me sometimes. So let's just look at them carefully. Equal means equal. Lateral means sides. So this is a polygon that has equal size. Equal means equal. Angular means angle. Equiangular. So just take your time pronouncing and make sure you're comfortable pronouncing these terms: equilateral, equiangular, and regular polygon. So what's an equilateral polygon? Well, I've drawn for you here a hexagon, or a six-sided polygon. That's 1, that's 2, 3, 4, 5, 6. Definitely has 6 sides. But this is no ordinary six-sided polygon. This six-sided polygon has all the sides that are congruent. So you see, each of these sides is equal in length. They're congruent to each other. So an a polygon that has all sides that are congruent like this, that's called an equilateral polygon. So I could have drawn a polygon something like this. That's 3, that's 4, okay, that's 5, that's 6. Okay, that's a concave polygon. That's a respectable polygon. Concave polygon is still a polygon, right? So that's a six-sided polygon of various different lengths. Or I could have drawn a polygon six-sided like this: 2, 3, 4, 5, 6. But these are all hexagons. But this one is special because all the sides are of equal length. If that's the case, it's called an equilateral triangle. So equilateral polygon, I meant to say. Equilateral triangle is actually the same thing. Equilateral triangle is an equilateral polygon. Okay, now equiangular means all the angles are the same. Okay, so let me draw over here. I'm going to try to draw, and now you have to take my word for it here. This is a rectangle. So a rectangle, if you remember, it looks like this. And it has all 90 degrees as sides. And I may be inaccurate in my drawing, but my intentions are good. And as they say. So this is equiangular. All the angles are congruent. So this is 90 degrees, that's 90 degrees, 90 degrees. So this is an equiangular polygon. So it's a quadrilateral, first of all. It's a four-sided quadrilateral. And I gave a special four-sided quadrilateral, and that's a rectangle. A rectangle is an equiangular polygon because all the angles are of the same degrees. They're all 90 degrees. They happen to be 90 degrees. Now, a regular polygon is one where both the sides are equilateral and equiangular. So a regular polygon basically is equilateral and it is equiangular. Okay, so it's both at the same time. Okay, let me give you an example of that. Look at this. This is a pentagon. Okay, and this is no ordinary pentagon. This is a pentagon that's equilateral. That means all the sides are of equal length, and also all the angles are of equal measure. So all of these angles are congruent. So here is a polygon that is both equilateral and equiangular, and that's called a regular polygon. So a regular polygon is super special in that it is both equilateral and equiangular. Observe over here that a rectangle is equiangular, but not equilateral, because even though these two sides are congruent, the opposite sides are congruent, but there are not all the sides are congruent to each other. So a rectangle is equiangular, but not equilateral. Now this happened to be a hexagon that is actually equilateral and equiangular. It's a regular hexagon, but it did not have to be. Okay, so allow me to give you an example of a polygon that is equilateral but not equiangular. Let's see if you can figure it out before I draw it here. Alright, here it is. I've tried to do my best here. You have to forgive me because it's not particularly accurate necessarily. But again, my intentions were good. Now what this is a rhombus actually. If you recall, a rhombus is a quadrilateral that has all the sides that are congruent like this. It's like a slanted square. All the sides are congruent. So it's equilateral for sure, but it's not equiangular. Clearly, this angle is not the same as that big angle, right? So this is an example of equilateral, but that's not equiangular. This is an example of equiangular, but not equilateral. All right, and when a figure is both equilateral and equiangular, it's called a regular polygon. So a polygon can be described as equilateral, which means all the sides are the same, or equiangular, which means all the angles are the same. And if both of these conditions are satisfied, then it's called a regular polygon. So let's review. We talked about it a lot today. So before we finish, just this review. So Polygons we defined previously as two-dimensional plane geometric figures that are closed, whose sides are made up of segments that are non-intersecting and non-collinear. Each vertex is common only to two sides. Okay, that was a basic definition of polygons. Then I suggested that there are two basic types of polygons. That is a convex polygon and concave polygon. Concave with a cave in or dent in the middle. And I talked about the line test, how if you extend any of the sides, then those would be going through the interior, and that's how you know a particular polygon is concave, or one of the interior angles is greater than 180 degrees. Then we talked about how one names polygons, and these are some basic names of the first 12 polygons. Three-sided polygon is a triangle, four-sided polygon is a quadrilateral, and you're familiar with many quadrilaterals such as a square, a rectangle, a kite, a rhombus that I have suggested, and five-sided polygon is a pentagon, six-sided hexagon, heptagon, octagon, nonagon, decagon, and hendecagon or undecagon, dodecagon, and anything beyond that, or you can just call it n-gon. So we talked about that naming of polygons. And finally, I talked about three special types of polygons. Equilateral polygons are those polygons that all the sides are of equal length. These are equilateral polygons. I gave you an example of a polygon that was equilateral but not equiangular. Here in a rhombus, all the sides are of equal length but not the angles. Equiangular polygon is one where all the angles are congruent, but the sides not necessarily are here. The example being this rectangle. And a regular polygon is one where it's both equilateral, all the sides are congruent, and equiangular, all the interior angles are congruent. A square actually is also another example of a regular polygon, because in a square, all the sides are congruent and all the interior angles are also congruent. Inshallah, next time we shall talk more about this and solidify our knowledge. Until then, as-salatu was-salamu ala rasulillah, walhamdulillahi rabbil alameen, assalamu alaikum.